Um, okay, how about woohoo for the hypercube, okay? Woohoo! All right, sounds good, okay. Because it's a cube and it's hyper. Okay, so, yeah, okay, we got a bunch of stuff to do. Okay, so for 3 space, the sphere is the object that minimizes the surface area to volume. Right? Does that make sense? The sphere minimizes the surface area to volume, right? So the surface area is sort of 4 pi r squared, and the volume is that. The ratio is 1 over 3r, right? So you have this extra factor of r, and that's sort of tight. It is sort of the thing that if you want to minimize the total volume, if you want to be warm in the Arctic, you should be a sphere, right? That's good, right? Because you lose the least heat that way. Okay. The graphical analog of that is to cut the graph into 2 pieces and find the ratio of edges and vertices on a small side. Graphs often do actually model like climate and various things, this is one of the things they look at. And we saw for the tree that it basically wasn't very connected at all. You could cut off very little surface area and cut off huge volume. You could cut many people apart by taking out one node. For the hypercube, it's actually, if you want to take out k people, you have to cut at least k edges. Okay? The surface area is roughly at least the volume. So it's a much faster growing object than the sphere, right? The sphere, as you get bigger and bigger, it's sort of the surface area starts to become less of the volume. But that's not true for the hypercube. The hypercube grows fast. Or at least a 3-dimensional sphere has this 1 over r. Okay? So remember, just for definitions, this is a hypercube. This one is a recursive definition, and that's what we're going to use. The hypercube over on the left is an 8-node hypercube, where all the vertices are correspond to 3-bit strings, and the hypercube on the right is also the same. It's 2 copies of the same. We extend their strings by 1 bit, and we add a 0 to all the vertices on the left, and we add a 1 to all the vertices on the right, and we connect them with edges. Okay, do you see a cut in this graph? Now there's a fairly, oh no, what's this, right? Okay, that's fine. That's on the next slide. Okay. So now we talk about a cut. Any subset S of the hypercube where the size of S is less than half, because it's not a cut at all if you take the whole graph. Right? There's no edges leaving all the vertices. So a cut means you split it into 2. So when you split it into 2, one of the sides is less than half. That's all this is saying. Though less than half. Okay? And it says that the smaller side has at least, if 5 people are on the smaller side, there's at least 5 edges leaving. If there's 100 people on the smaller side, there's at least 100 edges leaving. So that's what the size of S means. Okay, and this is just notation for saying the edges intersecting with pairs of vertices across the cut is greater than S. That's just notation that, may be helpful. So V minus S is a cut. Those are the cut edges. For any cut in the hypercube, the number of cut edges is at least the size of the small side. Here's a cut. You see this cut? How many edges are in this cut? Okay, so each vertex on the left has a partner in the right. Right? So how many vertices are there on the left? 2, 3, 5, 8. Right? How many vertices so how many edges leaving the left-hand side? 8. Right? So this theorem is tight for this cut. Okay? This cut gives you a tight example that says you can't prove a better bound. Okay? It says, here's a set of 8 nodes, and there's 8 edges leaving it. Does that make sense? That's the cut. And I want you to think about this cut a little bit because it comes up in the proof. Okay? It says, if you have the recursive definition, if one of the vertices over here is on one side of the cut, and that other one is on the other side of the cut, its mate, that gives you an edge in the cut. And that's what the proof is going to need to do. It's going to argue that there's a lot of edges in any cut. Okay? So it's going to use this recursive structure, and in fact, it's going to use these blue edges very heavily. Okay? To prove that there's a lot of edges like this leaving the cut. Okay? Now, there's nothing super special about these blue cut, right? I could have cut this way. I could have cut horizontally between the two, and that also has 8, right? You cut along, because that's just another dimension. In some sense, if you cut along here, in fact, these two are recursively 2 hypercubes too. The up and down hypercubes are also the top also form a hypercube, and as do the bottom. Okay, so there's many dimensions, right? It's d-dimensional. Okay, so here's the proof. The base case, if n equals 1, there's no edges, and that works. Okay? N equals 1 means, n equals 1 means there's 2 vertices, 0 and 1. So the only cut is cutting 0 off from 1, and there's 1 edge across it. Okay, so now we're going to use the recursive definition of the hypercube. 2 cubes are connected by edges. So we're going to divide it into 2 cases. We're going to think about sort of we're going to try to get our edges from inductively, right? We have 2 cubes, and inductively we know if there's a cut on each side, we get some edges, okay? And if for example we just cut off one cube entirely, we saw what happens there. There's a lot of edges going between the cubes, okay? Okay, so here's what the cut looks like. Here's one example, is where say the cut is really this corresponding cut here. So then all the edges going across go through nodes on the same side of the cut, so they don't help. But we can use the inductive edges in this inductive proof to say there's a lot of edges. Okay? Case 2 is, okay, so now it's not quite matched up. It's like, okay, S, the size, this is the size, the top thing. S is the thing we're cutting off. We're assuming that's less than half. But on this side, it's actually taking more than half. And on that side, it's taking way less than half. Okay? So since this is taking more than half, you don't know that there's a lot of edges to this other side. It's not going to be proportional to S. In fact, the number of edges here is proportional to V minus S, the size of V minus S. Right? Because this is the small side in this recursively smaller cube. So all we can say in terms of the number of edges that cross this cut are the number of nodes in this small side, not the number of nodes in S. Okay? But we get saved. We get saved by these edges. If this size is bigger than this size, then you know there's some nodes over here whose partner is on the other side of this cut. So we count them. Okay? Those are those blue edges I showed you on the last slide. Okay? That's the proof. And the rest is just algebra. Okay? Here I imply induction. There I'm assuming one of the sides is bigger than half, so I can't apply induction. So then I imply the induction to argue about this plus this plus this. Okay, so case 1. Okay, these are recursive definitions just to get it set up. There's the vertices and edges in hypercube 0 and vertices edges in hypercube 1. The whole hypercube is the union. Now I'm thinking of S0, where S0 is a subset of V0 and S1 is a subset of V1. It's just exactly this picture we said. Okay, so now we say case 1. We're going to say this is one case where we take the number of vertices S0, the size of S0 is less than half the vertices in hypercube 0. And the number of vertices in hypercube 1 is less than half the vertices in hypercube 1. Okay, in S. So then we could just apply induction. We know that the number of edges in this edges cut in H0 is greater than S0 by induction. That's what it says. It's at least the size of the small side. We know that S0 is a small partition of V0, so there must be a lot of edges going from S0 to V0 minus S0. Okay? And similarly for H1, we add it up, and that's what we get. Okay. I used to play the Violent Femmes at this point. They had this song, Add It Up, and I would say, add it up, and okay, well, never mind. But now the YouTube will turn off your video if you have copyrighted material, which makes students, well, the 3 students who watch it makes them sad. So, okay. So the other case is that S0 is more than half, right? So this is what the picture looks like. It looks like S0 is more than half, S1 is less than half. Why does S1 have to be less than half if S0 is more than half? What's the size of S0 and S1 together? Less than half. So if this is more than half, this better be less than half, right? Okay. So recall case 1, S1 is less than V over 2. So here, S1 is less than V over 2 since S is less than V over 2, right? That's the argument I just made. The size of S plus the size of S0 is at most V over 2. And now if there's too many nodes in here, then S1 can't be too big. Okay? So that tells us these edges here, these 3 edges, is really the size of S1. Okay, so we're just counting these 3 edges that I've drawn here. Okay, now S0 is greater than V0 over 2, which tells you that this piece down here, this V0 minus S, is less than half the vertices in this subhypercube. So since it's less than half the vertices in the hypercube, we can say the number of edges coming out of this set is at least the size of V0 minus S. Now remember, V0 minus S, okay? So V0 minus S0 edges are cut in E0. Okay? Okay, now finally, now we're going to count these edges across. Edges in EX connect corresponding nodes. So whatever nodes over here, there's some nodes that there's every vertex here has a partner over there. There's only S1 partners over there. So at least some of these S0 nodes must have a partner over there, which is on the other side of the cut. Okay? And that's the amount. It says I have the number of guys in S0 minus the number of guys in S1 have no partners on the other side in S. Okay? So these edges don't go to S. They go here. They go to the other side. So we get to add them because they cross this cut. And now we just add those 3 together. S1 plus V0 minus S0 plus S0 minus S1. And that, these things all cancel. I get V0. Okay? And what is V0? Is V0 at least half the number of edges in the cut, half the number of vertices in the whole hypercube? Yes. So in this case, we have more than half the vertices in the whole hypercube, which is bigger than S. Okay? Okay, so that's the proof of this theorem. Okay. Yeah, there's a case 3 where you can, it's without loss of generality, you can just argue S0 is that V1 is this side had more nodes in it on S. Okay? Okay. Okay, so good. The cuts in the hypercube, exactly the transitions. Now, if you think about a hypercube, why are we obsessed with a hypercube? The hypercube is the 0-1 strings. I used to be a physics major. I stopped being a physics major. One of my buddies who was a physics major would chant at me because he thought it was funny. Zeros and ones, that's all you do, zeros and ones. So it's true. Okay, I have to confess. As computer scientists, we work with computers and there's bits and we're working with this, right? And so what we work with, our programs take in bits. And they answer maybe many things, but let's say they answer 0 or 1. That's it. Yes or no. Okay, they're Boolean functions. Okay? Boolean functions are exactly cuts in the hypercube. Which subset of vertices do you label 1? And which subset of vertices do you label yes? And which subset of vertices do you label no? So they're central to computer science in many, many deep ways. And we'll see it in error correcting codes, and we'll see it, and if you go to grad school in complexity theory, this is what you will be spending your life with, the hypercube. But anyway, so that's yes, no. It's a central object study. So that's why we think it, and it's really just a beautiful graph. Okay, so next up is modular arithmetic. Okay, if it's 1 o'clock now, what time is it in 2 hours? Okay. What time is it in 5 hours? 6. What time is it in 15 hours? Yeah. Or 4. Okay? Right? Here in this country, it's 4. Okay? So, usually. 16 is the same as 4 with respect to the 12-hour clock system. Right? Clock time is equivalent up to addition and subtraction of 12. That's this notion of clock math, right? What time is it in 100 hours? Do we know? What time is it in 100 hours? 101. No, we clearly don't do that, right? It's 5 o'clock, right? Because 12 times something is 96, and then that gives you 5 remainder. Okay? This is what I'm saying. It says every 12 hours I go back to the same time, right? 5 is the same as 101 for a 12-hour clock system. I'm letting you say 101, but I'm just going to call it the same. You say 101, I was like, yeah, 5. Okay? This is the communication we're going to do. Okay? In clock math, 5 and 101 are the same. 16 and 5 are the same. 16 and 4 are the same. Okay? So those you can have all the natural numbers. I'll let you have them, but they're all equivalent. When you add 12, modulo adding 12. So the custom is we usually only represent in modular arithmetic the numbers in this range, 0 through 11. So it's remainder. Clock math is really remainder arithmetic. You divide by 12 and you see what your remainder is. That's your time. Except for 12 is used instead of 0. But if you think of it, 12 is 0, then it's really just the remainder when you divide by 12. That's what clock math is. Okay. So we can do this with the day of the week. There's Tuesday. What day is it a year from now? Oh, somebody knows. Is that February 12th? Is it February 12th? I don't even know. So you number the days, 0 for Sunday, 1 for Monday. I changed all these numbers. I tried to get it right, but we'll see. When I change the numbers, it's always iffy. So today is day 3. Oh yeah, I did it wrong. Today is day 2, right? Okay, let's assume it's day 3. Okay, I can't count. 5 days from now is day 8. Okay, what do you do now? What day is that in this system equivalent to? Day 1, right? You subtract 7. We're doing week math instead of clock math, or Monday. Okay, 25 days from now is day 28 or day 0, right? Because I'm just taking the remainder when I divide by 7, or I factor it and I see that 7 times 4 is equal to 28. 2 days are equivalent up to the addition and subtraction of a multiple of 7. 11 days from now is day 0, if it were day 3, which is Sunday. What day is it a year from now? This year's not a leap year, so 365 days from now. So day 368, which I don't know what that means. So then I bring it back to the range between 2 to 7. Subtract 7. I keep subtracting 7 until I get to something that's smaller than 7. Divide and get the remainder. Okay? That's it. So it's day 4. So it's 1 day more. So I guess that would be Wednesday. But I got the 3 wrong. I thought today was Wednesday for some reason. Okay? Okay. So 80 years from now, right? You can see where this is going. Okay. 20 leap years, roughly. I don't know. I didn't really count. 366 times 20, 60 regular years, 365 times 60. Today is it day 2 now? It is day 2. Okay. Oh, but it's day 3. Yeah. Equivalent to. What is that equivalent to? Okay, so I don't know. What's the remainder of 3? Okay, so that's we can multiply it out and then divide by 7. But you know what else you can do? There's a point to this one. Okay? I was like, what's the remainder of 366 when dividing by 7? 2. Right? What's the remainder of 365 when dividing by 7? 1. Today is day something. And now what I'm doing is I'm changing the 366 to a 2 and the 365 to a 1. I didn't want to do that multiplication, right? But in fact, I don't have to. I can just translate it all back to the 0, 1 and then do arithmetic using small numbers, okay? This is one reason why modular arithmetic is important in computer science. When you multiply things together and together, you get bigger and bigger numbers. If you mod out, you do not. Okay? Okay, so remainder when dividing by 7, you can go on. It does something. It's a Friday, or maybe. I would guess I'm off by 1, so it would probably be a Thursday. But you can keep doing this. You don't have to. I could have done it here too. I could have made this go down to 20. And look, I get 19. And I better get the same result. The point is I better get 5 here. And I do. Right? Once you divide 19 by 7, I get 2 times 7 plus 5. And that's is equal to 19. Okay? Okay. Okay, so you can, yeah.
Do you have to do it to the whole equation if you're going to do it to one number?
No. No, you can do it any way you want. Okay. Reduce at any time, any place in the calculation, right? Okay. So if x, and let me prove that. Okay, so now if x is congruent to y, we have this notation, modulo m. X is congruent to y mod m. If and only if x minus y is divisible by m. Okay, that's what it's saying. Okay? So just math that says the same thing. Like 1 is congruent to 8, because 8 minus 1 is 7, right? And 1 is congruent to 8 mod 7, because 8 minus 1 is 7, which is a multiple of 7. Okay? Another way to say it is that x equals y plus k times m for some integer k. So the integer can be positive or negative. Okay? So mod equivalence classes, this is one equivalence class, 0 and 7. So sometimes mathematicians will work with 0 through 6 as the elements of modulo 7. But we could also just say all the integers can be seen as elements of mod 7, but they're equivalent, right? 0, 7, 14 are equivalent. Negative 6, 1, 8, 15 are equivalent. This infinity of natural numbers are really just one thing under this arithmetic system. And that's why the 3 bars. It's the equivalence thing. Okay? Addition, subtraction, multiplication can be done with any equivalent x and y, modulo 1. Okay? So A equals C mod m and B equals D mod n. That says that it should say that A plus B equals C plus D mod m, and A times B equals C times D mod m. It says whatever representations you work with is fine. Okay? And let's prove one of these. If A is equal to C mod m, then A equals C plus km for some integer. Again, we use our equality, right? This is what the definition is. If B equals D, we get B has this form. Therefore, A plus B equals C plus D plus K plus J times M. K is an integer, J is an integer, so K plus J is an integer. So C plus D is equivalent to A plus B mod M. Okay, so it's an easy exercise. Okay, so it says you can work with any representative in these equivalent groups, and it's fine. Okay, these are in some sense the easiest, 0 to m minus 1. Okay, so notation, we x mod m or mod xm. What we mean by that is actually the remainder of x divided by m in this range. So I'm just going to use notation in my slide. I'm just telling you what it means. If you get confused, you can ask me. So mod xm is just x minus the quotient of x and m, floored, times m. Okay? It's just the remainder. It's just a formula for the remainder. Is that clear? It's a floor x 42 or 43. The floor of 43 divided by 7 is 6. And you get a remainder of 1. Okay? So this x over m is a 43 over 7, which would be a 6. Right? That's what the floor signal means, the next smallest integer less than that fraction. The largest integer no larger than the fraction. Okay? So you can see this, right? 29 is equal to this. And I think that's right? 29 divided by 12, the quotient is 2 when you round down, which is equal to 4. Right? Nobody? It's not equal to 4. Okay, so nobody? Huh? Okay. Okay, so we work in this. That was a joke, right? I had a 4. It's not a 4. It's 5. Okay, so it says 2 integers A and B are equivalent mod m. Modulus is m. That's what we call the modulus. 6 equals 3 plus 3 equals 3 plus 10. Now, this is what we do. We don't say 6 mod m is equal to 3 plus 3 mod m, which is equal to 3 plus 10 mod m. The whole system is we're working in this arithmetic. And I'm using 3 equality signs here, but it's not important. You can use 2. It's not a big deal. But we generally put the mod way out at the end of the equations just to make it cleaner. Okay? And so on. Right? Generally, we don't put the mods in the middle, right? Because it's unpleasant to the eye, right? Because we're working in this whole system, so we just put that over to the right. Okay? We don't take off points for that. But it makes it hard to read. You should do it the way we do it. It's better. Okay? Okay, so good. So now we have this whole new, you have this arithmetic system, and we've worked with another one all our lives, right? The real numbers or the rational numbers, right? So let's understand how this particular thing works, right? We learned lots of cool things with the rational numbers, right? You can solve linear equations, right? 3x equals 4. You could do various things in them. What carries over to this system of arithmetic? That's what we need to see. Okay. So remember, right? This is what we had forever. 2x equals 3. What's the question there? As soon as I say 2x equals 3, you guys say 3 halves. Right? It's obvious what the question is, right? What's x? Okay, and it's obvious and the way we do it is we do this thing called multiply by the multiplicative inverse. Who remembers your teacher saying that? Multiply by the multiplicative inverse. Some teachers would say divide by 2, but many, many times they also say multiply by the multiplicative inverse, because mathematicians designed K through 12 education, at least in some part, and they said, no, you need to tell them to multiply by the multiplicative inverse, and you'll see why. Okay, they are preparing you to take this class. Okay, that is why. Okay, so remember this. It's very important. What you do to get rid of that 2 is you multiply by the multiplicative inverse of 2, which is 1/2, and then the 1/2 times a 2. And you have to do both sides because it's an equality. Whatever you do to one side, you should do the other side, and then you get 3 halves. Okay? So what is the multiplicative inverse? Okay, the multiplicative inverse of x is whatever y is that x times y equals 1. Okay? Okay, so 1 is a multiplicative identity element. That's what they call it. And in modular arithmetic, 1 is still the multiplicative identity, right? If you multiply by 1, you just multiply the representative by 1. It doesn't change, right? We're still using the axioms of arithmetic with the natural numbers. Multiplication means what it means. Addition means what it means. This notion of equivalence is added on top. Okay? So the multiplicative inverse of x mod m is y, where in this arithmetic system, x times y is equal to 1 mod m. So x times y could be 1, but it could also be m plus 1, right? Or 2m plus 1, or whatever, right? Any equivalent representation. Okay? Okay, so for modulo 7, the inverse is 2. How do I know that? I don't. Okay, but I can multiply. I can multiply 2 times 4. I see that it's 8. And I see that 8 is equivalent to 1 mod 7. And then I know it meets the definition of multiplicative inverse. Right? 2 is the multiplicative inverse of 4, because when I multiply 4 by 2, I get 8, which is equivalent to 1 mod 7. Okay. So now, what did I want? I was like, what is x? 2x equals 3. That's what you were trained to do all your life, right? And so now we want, what is x? 4x equals 5. What do I do? Well, I multiply both sides by the multiplicative inverse. Okay? So, and then I get 8x on one side, I get 10 on the other side, I get x on one side, 10 I'm reducing mod 7 using the representative between 0 and 6, and I get x equals 3. Now, what else did you do in elementary school when you solved equations? Yeah, you plugged in, right? So let's plug in and make sure it's all working, right? 4 times 3 equals 12. 12 is equal to 5 mod 7. So 3 as a value of x seems fine. It does satisfy the equation that 4 times 3 equals 5. Yeah. Where did the 8 go? Yeah. Yeah, where'd the 8 go? You saw it's there? Okay, good. Okay, so I subtracted 7, right? Any equivalent representation. I could have gone to 15. But, just it's more, we're going to do the way that makes sense, which is 1, right? Okay. I mean, sometimes it's just more convenient to always work with the things between 0 and n-1 and always use the remainders. But when you argue, if you say those are the only things you're working with, in the proofs it becomes complicated to discuss. That's why we have these two views. Yeah. What? No. No. Don't do that. Okay, so can you multiply by 1 over 4? Don't do that. Okay? There is no 1 over 4. It doesn't exist. Okay? I mean, it did, unless you want to use it as notation for 2 mod 7, that's fine. But don't do 1 over 4. Okay. There is no 1 over 4. It's only, the only things are 0 through n-1 or the equivalence class of integers. Okay, you do that, you won't be happy on your grade for the exam. And people do it every year, and I make this speech every year. Please don't do that. Yeah, it's not going to work. Yeah. He's asking if the number has only one multiplicative inverse. What do you think? Is it they're multiplicative inverses of each other, right? So, what do you think? There's a no. No, there won't be. There won't be. But I'm just trying to come up with a quick argument. I mean, there will be an argument. There'll be many arguments in the slide, but I'm trying to come up with the simplest one. I don't know the simplest one. It's a function, right? When you multiply by x, it's a function. The inverse function is multiplied by y. Okay, so you can't have two different inverse functions. Right, because they're 1-to-1. Okay, but that's the argument that I'm going to make, but I don't know that that's that simple to see. Okay? Okay, so multiplicative inverse is this, so we did all this, right? Okay, good. Okay, so now what we can do is, so I did that one, so let's try this again. Let's change up the problem in again. For 8 modulo 12, there's no multiplicative inverse, and I'm going to prove that. That's the proof. Right? Do you see? Why is there no multiplicative inverse for 8 mod 12? What is 8? It's a multiple of 4. What is 12? A multiple of 4. Whatever you multiply 8 by, what are you going to get? A multiple of 4. Is that ever going to be a multiple of 12 plus 1? It's always going to be at least 4 away from any multiple of 12. Right? Does that make sense? 8k minus 12l, right? What you have to do to make k be the multiplicative inverse is you have to be some integer multiple. You have to be 1 away from an integer multiple of 12. That's what this is saying. So this is always a multiple of 4 for any. So 8k can't equal 1, right? This expression can never equal 1 because there's always a 4 here. You factor out the 4, and then you get 2k minus 3l. And 4 times an integer is always going to not be 1. Okay? Okay, so if they have a common factor that's bigger than 4, there's no inverse. There's no multiplicative inverse. Right? Okay. Okay, so now the flip side of the theorem is if the greatest common divisor of x and m, GCD of x and m, is 1, if it's not bigger than 1, if the greatest common divisor... If they have a factor that's bigger than 1, no inverse. Mod m. No inverse for x mod m. Okay? We saw that. If they have a common factor, you're always going to be one of those common factors that's going to be there. Okay, so now this is the other side. That's the only problem. Okay, if they have no common factor bigger than 1, then there is an inverse. Okay? And I'm going to use this bijection proof. It has to do with what he was saying, asking. Okay. Okay, so I'm going to write down all the numbers. I'm going to try everything. I'm going to do the elementary school thing. 0 times x, 1 times x, 2 times x, 3 times x. What I'm looking for, if I ever see 1 in this set, then I found the multiplicative inverse, right? Because I'm trying everything. I'm multiplying by 1, 2, 3, 4, x. And then if I get some, say 5 times x is 1, then 5 is the multiplicative inverse. Okay? So if this set contains 1, okay, if the set is all different, that's what it's saying. If the set is all different, then it contains 1 mod m, right? Each of the m numbers correspond to a different one of m equivalence classes. That's what I'm saying. So one of them must correspond to 1 mod m. So what I have to show is that this function, that where I multiply by x, that's what I'm doing inside of this S. I'm multiplying every element of 0 through m minus 1 of our arithmetic, domain by x. Okay, so that's that function. So what I want to say is that function is bijective. They're all different. Okay, that's what I want to prove. If they're all different, then I know there's a multiplicative inverse because 1 must be in there by the pigeonhole principle. Okay. Okay, so here's the proof of the claim. Why are they all different? Okay, so what we want to say they're all different. That seems hard. So we say, okay, let's just assume 2 are the same. Okay, and see if we could find a contradiction. Okay? If not distinct, there exists a and b in 0 through m minus 1, where a doesn't equal to b, where ax equals bx, right? This multiplying x by a and multiplying x by b gives you the same number, modulo 1. Okay? So now we can just we can do regular arithmetic here, right? It's a minus b times x, which is equal to 0. Okay? Now what that tells you is that if it equals 0, it's a multiple of m. Right? A minus b times x is a multiple of m. That's what it means to equal 0 mod m. It means the remainder when you divide by m is 0. So it's an exact multiple of m. Okay? So look at the 2 blue things. So you should be able to follow that step. A minus b, quantity times x is equal to 0. A minus b times x equals k times m. Okay? Now, the GCD of x and m is equal to 1. So what does that imply about x and m? I highlighted x and m. So I'm going to write the prime factorization of x and m. Okay, we did that in the first lecture. This course is very connected. So we said we could write x as a prime factorization, we could write m as a prime factorization. Do they have any factors in common? Do they have any factors in common? They do not, right? Because the GCD is 1. They have no factors in common in their prime factorizations. But somehow over here, and you see this m over here? Somehow all the factors have to be over here on the left. Right? Because they're not in x, but they must be at least in a minus b, because there's an equality. So whatever the factors there are in m, this prime factorization is unique. There's only one way to write it down. So once you write it down, it has to contain, the left-hand side has to contain all the factors of m, even with multiplicity. Okay? So a minus b, if you look at the prime factor, that's just an integer, and you can write down its prime factorization. It has to contain all the primes in m's factorization. Okay? Because they have to be somewhere on the left-hand side. There's no factors of m and x, so they must all be in a minus b. Now, if you that tells you a minus b has to be a multiple of m, because a minus b has to contain all the primes in m's factorization. So it has to be a multiple of m. But a minus b is greater than or equal to m then. But what did we assume about a minus b? A and b are between 0 and m minus 1. Okay, so they're close to each other. Okay? So, and that's a contradiction, right? A minus b can't be greater than or equal to m and be inside of 0 through m minus 1. Now, it could be a representative, but we can choose a representative. We chose to use representatives in here. That's fine. Okay? And that's the proof. So, this is a bijection proof, right? It says when you multiply by x, that's on the domain, which is that you're working with, mod m, 0 through m minus 1, you get different elements of the equivalence class. And one of those elements must be 1 by the pigeonhole principle, because they're all in the equivalence class. Okay? Okay. So, just a quick review. I always think that if we could teach a computer bijections, they would be able to do discrete math. That's why I'm really obsessing about this. A lot of our arguments are that. That's what the handshake lemma is, 2e times the sum of degrees. So that's why I'm just going over these arguments so you can make them. Right? That's what that nasty stable marriage thing was with the r and the r prime. Yeah. So, okay. So, I'm not going to do the proof, but I'm just going to show you an example of what the proof did with examples. Okay, so for x equals 4 and m equals 6, what are all the products of 4? S equals all of these. Now, what the claim in the proof was that they're all distinct. Okay, these are not going to be distinct. Why are they not going to be distinct? Because what do 4 and 6 have in common? Factor of 2, right? So we have all of these. They look distinct to me. Why aren't they distinct? Because I haven't modded out by 6 in the way that I can easily tell. They're not distinct, right? So, okay, 5 and 6, we have all these things. We have these numbers. You see now, what is the multiplicative inverse of 5? You see this? Here's this set. Where's the multiplicative inverse? Well, it's whatever you multiplied 5 by to get 1. What did we multiply 5 by to get 1? It was 5 times 5, right? So what's the multiplicative inverse of 5? What's the multiplicative inverse of 5? 5, right? Another way to see it is 5 is also negative 1 mod 6. So it turns out that's easy too. Okay? So 5 is the multiplicative inverse of 5. Yeah. What normal number is its own multiplicative inverse? Is there a number that's its own multiplicative inverse? 1. Yeah. Is there another number that's its own multiplicative inverse? What's negative 1 times negative 1? 1. Is 5 negative? Is it equivalent to negative 1 mod 6? It is. So this wasn't an accident, right? 1 and negative 1. Okay? So 5x is equal to 3. What is x? You multiply by 5. You get 15, and you check. What about this? 4x equals 3. Now 4 and 6, they don't have a common fact. They have a common factor bigger than 2. And in fact, this doesn't have that common factor. 3 does not have 2 as a common factor. So there's no solutions. Okay? You can't get an odd. That's the argument. Okay? So 4x equals 2. This one, maybe there are solutions here, right? Because you know that this is going to be some multiple of 2. It's going to be even. And in fact, there's 2 solutions. Okay? There's 2 solutions to this problem. Okay? So it's once you have common factors, it doesn't work like you think it does anymore. Okay, but if you do have common factors, it really is, you can have inverses. Okay? Okay, so so you can do stuff. You can solve equations at least if when you're only dealing with things that are kind of relatively prime. Okay. Okay, so let's just review this again. GCD of x and m is 1. Then the function f of a times of multiplying every element by a is a bijection. 1 to 1. There's a unique preimage, right? Onto the size of the domain and the codomain are the same. So for x equals 3, m equals 4, f of 1 is equal to 3. This should be a bijection, right? We're multiplying all these numbers by 3, right? That's what x is. And f of 2 is equal to 6, 2 times 3, and so on. Now, those are all different. You also have to do 0. Now, for this one, it's a unique preimage and the same size. So that's why it's a bijection. Okay, all the images are distinct. is it means there's a unique preimage for any image. Okay, and here you'll see that you have that the domain is mapped, instead of to the entire domain, it's mapped down to just a subset of the range. Okay, the range is a subset of the domain. So you're only mapping all of 0 through 3 down to either 2 or 0. It's not a bijection. Okay, so that's an inverse. And how do we find an inverse? Let's give you a quick break. Okay, I'll give you a quick break. How do you find an inverse? Okay, so there's always, well, we saw how to find an inverse. You just try everything. Okay? You find the GCD, how to find if X has an inverse. First we can find if, we can just tell the GCD of X and M, right? Is it greater than 1, right? That's all we really have to do. Okay, there's no multiplicative inverse. Okay, so, if it's equal to 1, then it's a multiplicative inverse. That's what I said. That's the proof of the theorem. So the algorithm is you try all the numbers up to X to see if it divides both X and M. Do people see a problem with that algorithm? What if X and M are huge numbers, 100-digit numbers? Who would want to do that? Yeah, well, right? I mean, that's the problem. It's very slow. Okay? So we're gonna talk about Euclid's algorithm, which is really fast comparing trying all the numbers. Okay, so just to be ready, does 2 have an inverse mod 8? Okay, any multiple of 2 is 2 away from 0 plus 8k. I'm telling you the same arguments many times, so you see them many times, right? Does 2 have an inverse mod 9? Okay, and that's because it's 5. Okay, does 6 have an inverse mod 9? Right. It's a multiple of 3. Okay? No. Right? Yes. Okay? It's only if GCD of X and M is 1. Okay. We want to compute the GCD. And then we want to compute the actual inverse. Okay? So that's the next 2 things we're going to do. So we're going to remember our first lecture again. D divides X means D divides X. Or X equals KD for some integer K. And this is, I think, one of the first proofs we did. We said if D divides X and D divides Y, then D divides X plus Y and D divides X minus Y. Okay? Is it a fact? Yes? Yes, it is. Okay? Here's the proof. D of X divides D of Y. What do? We translate it in equations to write the proof, right? As soon as you think about, I have to prove this, there's some sort of nervousness that happens, and it's like, how do I set it up? Here, how you set it up is you write the equations that correspond to those things, to divides. And now once you write divides, you could write x minus y quite easily, and you can also write the right-hand sides, the expressions corresponding to the right-hand sides, and take their difference. You factor, and what do you see? Does d divide x minus y? Yes, because k minus l is an integer. Okay? Using the definition to get into equations and using the definition to make our conclusion. Okay, so notice x minus y is smaller than x and y and has same common divisors. Okay, does that tell you something now? This fact is useful. It's just not some random fact. Right? I'm going for an algorithm. Right? Does this suggest an algorithm? I say the greatest common fact, I want to produce the greatest common divisor of x and y. Now look, x minus y is smaller than x and y, maybe. If it is, then I can actually just produce the greatest common divisor of y and x minus y. Is that easier? Well, at least one of the numbers is smaller, right? So I've made some progress, right? You should be thinking induction or recursion at this point, right? Does that make sense? Like immediately this fact says, oh, look, this is an amazing fact. Look, d divides x and d divides y, but let me pick these two. D divides y and d divides x minus y. Now, if x minus y is smaller, which it usually is, then now I have a procedure that only needs to work with y and x minus y, which is smaller. So I can assume it works by induction. Okay? So that's Euclid's algorithm. But we can also do this a little bit more, be a little bit more aggressive about how to make it smaller. We can say if d divides x and d divides y, then d divides y. The d divides y, then d divides y is a very easy thing to prove. But d divides x and y, then we need to say it divides this mod. Okay? The mod is the remainder. Remember, it's a remainder of x divided by y. Okay? Which has this form. So that x over y is some s for some integer s. Okay? Now y is divisible by, y is divisible by d, so we can replace it by an integer times d, and x is as well. That's what we did here. Now we can factor out, and we get our result. Okay, d divides mod x and y. Okay? And the second thing in the conclusion is d divides y. Okay, so we can be even more aggressive. We don't only, I'm just setting up this induction, this recursive procedure. Okay? When I want to find, I can go the other way too. So if d divides y and d divides mod xy, then d divides y and d divides x. So this is an if and only if. Okay? So what it says is that the GCD of x and y is equal to the GCD of y and this expression, which is the remainder of x divided by y. Okay? That's already it. Now we're done, right? This is a recursive procedure. Is that clear? Okay, and the idea is that x and y have the same set of common divisors as x and mod xy by lemmas 1 and 2. So anything that divides x and y also divides y and mod xy. Anything that divides y and mod xy divides x and y. And it's really exactly the same proof. The proof goes in the reverse order. Okay? So if they have the same set of things, if I have numbers 1, 3, 5 here and numbers 1, 3, 5 here, they're the same set. The largest in both sets, the same set is going to be the same. Okay, so that's what the theorem says. Okay. So what is GCD of 7 and 0? We have to do one more part to get a base case. To get an induction. You have to do a what case? I just told you. Okay, so base case. We have to do the base case. So the base case, this is what is GCD of 7 and 0? What is the largest factor? What can you multiply? What is the GCD of 7 and 0? It's got to be one of two things, 0 or 7. But you should say 7 because it's 7. Okay? Right? Because since 7 divides 7 and 7 divides 0. Right? Because 0 times 7 is equal to 0. Okay? It's an integer times, 0 is an integer times 7. Okay, so GCD of x and 0 is what? X. Okay? So now we have our whole thing. We look at this is the thing. People are amused because I guess it's scheme. It is scheme or some version of Lisp. Okay, so Euclid of xy is if y equals 0, then you return x, right? That's the base case, and the recursive call is exactly the mod GCD theorem, right? Scheme is way better. You were deprived by not learning 61A in scheme. There's really, my heart breaks for you. But there's a reason. I can tell you if you want at another time. So I want to say that this equals GCD of x and y, if x is greater than y. So here I'm assuming that x is greater than y. Why am I assuming that? Because otherwise this mod xy doesn't really make x smaller, right? And now I'm enforcing it by saying, look, what mod xy is smaller than y, right? It's in the range 0 to y. So I'm enforcing this invariant that the first argument is larger than the second argument. Okay, for this procedure. Okay, if y equals 0, then we're done. X divides y and x, so x is a common divisor and clearly the largest, right? Because x is greater than or equal to y. Okay, now the induction step, mod xy is less than y, which is less than x. So therefore, it's valid to call this program with the arguments in this order, right? I made it so that the larger argument is first and the smaller argument is second. Okay. And by the strong induction hypothesis, this recursive call computes GCD of y mod xy, which is GCD of xy by the GC mod theorem. Corollary. Okay? So it's simple. So the whole rest, this proof is just sort of the wrap-up of what we were doing in a couple of previous slides. Okay? Okay. So let's look at the running time. I claim this is a lot better than checking every number. If you have a 100-digit number, it's a lot better than checking every number up there. Okay? So now I want to say, what's the value? I want to think about numbers and what does it mean by their size. So how big is, I believe that's 1 million. How big is 1 million? What does that mean to you, 1 million? Well, for me, as a computer scientist, it means 7. Okay, because there's 7 digits in its representation. 1, 2, 3, 4, 5, 6, 7. Right? Or really maybe 20, because it's 20 bits in its representation. So I don't think of, so there's 2 ways to view a number. One is what is the value? What is the value of the number? It's 1 million, obviously. Okay? The value of 1 million is 1 million, right? But what is the size of 1 million? Well, for computer scientists, we don't care about the value. We don't care what anything means. We just care how much space it takes, right? So when I'm being a little facetious, but not really, right? This is, it's going to be super important. Well, we work with 500-digit numbers all the time. Every time when you're surfing on your phone right now, you are using RSA, and your phone is doing all of these GCD calculations with 100-bit numbers or 500-bit numbers, right? All the time. Okay, so we can't afford that other GCD. 500-bit numbers would be bad. So the number of digits in base 10 is 7. The number of bits is basically 20, 21. We round to 20 for some reason. For number x, what is its size in bits? So now I want you to understand the conversion. Now we'll do this more later in the course, but you should at least understand this conversion. So n, what I think of n as is the size of my input as a computer scientist. How many bits does it take me to write down my input? And it's basically the number of bits of x. Now I think of x as the value of that number. Okay, so x here is 1,000,000. So the size of the million, which I'm representing n, at least on this slide, is log base 2 of x. Okay, that's just what it takes to represent a number of 1,000,000 takes log base 2 of 1,000,000. 1,000,000,000 takes log base 2 of 1,000,000,000. That's about 30, and so on. There's roughly 10 bits per 1,000, because 1024 is 2 to the 10th. Okay, so log base 2 of x, it's just the exponent. You write it as this is roughly 1,000,000 is 2 to the 20, so you take the log, and that's 20. Okay? Okay, so that says, now if you have a number xy, I'm thinking of n as the size of the numbers, the number of bits I have in the representation of x or y, the max, some number n that's larger than the representation of the number of bits in x or y. Okay? Okay, so is this good? It's better. Is it even better than trying all the numbers? Do you see that it's better? Okay, if you do this algorithm, the y is approximately x. Let's just assume that. It roughly uses y uses n bits. So there's 2 to the n minus 1 divisions, right? So you'd much rather do 2n divisions than 2 to the n minus 1, right? 2 to the n minus 1 goes very fast. For a 100-bit number, 2 to the n minus 1 is a lot of divisions, okay? 10 to the 30, it's a lot of divisions, okay? 2 to the n is much faster, right? Roughly 200 divisions. So you'd rather do 200 divisions than that number. I mean, pretty soon, if you try to do it for RSA, it's more than the size of the universe, or more than the nanoseconds since the beginning of the universe, blah, blah, blah. Okay? But it's big. It takes a long time. Okay? Okay, so trying everything, let's do that. Okay, so that's bad, right? We don't like trying everything. What does GCD do? Here's what it's doing. And it's making progress. It's making serious progress. Look at the first call. So those are kind of big numbers. Look at that call. Look, that got a lot smaller. Like 132 is a lot smaller than 700, right? It came from the 700, all right? It came from the x. And now we put it back. Forget the line in the middle. That 132 came from the x. So 700 went to 132. Now, the second call down, 132 is less than half of 700. And so on. 40 is less than half of 568. 12 is less than half of 132, and so on. It's really fast, right? Didn't take 700 divisions, didn't take any, right? It took very few. Okay? The first argument decreases pretty rapidly, right? If you just look at it, it's kind of hard to understand because there's 2 arguments, but it's decreasing rapidly. So it's at least a factor of 2 in 2 recursive calls. So the 700 went over to the 132, which then, in the next thing, it just got swapped by the algorithm into the first position. Okay? Okay, so now the first argument, now this is the fact I want to prove. If the first argument decreases by at least a factor of 2 in 2 recursive calls, I'll prove it on the next slide. After 2 log base 2 of x, or order n recursive calls, the argument x is a 1-bit number. Once you're at a 1-bit number, you're basically done. Okay? Okay. 1 division per, and there's 1 division per recursive call. This mod divides the x by y. Right? And the division is the most expensive operation. Okay? So so all we need to do to finish is to prove this fact. The first argument decreases by at least a factor of 2 in 2 recursive calls. Okay, so the first argument decreases, okay. First of all, you see that the first argument sort of decreases every time, or at least gets no bigger, right? Because look at the code. You go from x to y, your assertion is that x is greater than y. Okay? And the second call, and this first call inside, y goes to the first one, so y is no bigger than x was in the beginning. So the first argument between these 2 recursive calls, the top one and this one inside, y is less than or equal to x. Okay? Now let's think about 2 cases. If y is less than x over 2, the first argument is y, so it already decreases by a factor of 2, and we're happy. Okay? If y is really small compared to x, we're done anyway. Okay? Okay, now, if y is greater than x over 2, we want to say that the second argument is really small, because that second argument will then become the first argument in the next recursive call. This is just slightly confusing because it's off by 1. Okay? So this mod xy in the next recursive call will be the first argument. So we're going to show that mod xy is less than x over 2. And the intuition is that mod xy is at least, you could at least subtract y. When you're dividing by y, and taking the remainder, it's going to be at least as small as just subtracting y. You might subtract 2y. Okay? Okay. So the mod xy is the second argument in the next recursive call and becomes the first argument in the next one. Okay, this is the final thing. When y is greater than x over 2, x over y, this floor, is 1. So mod xy is just x minus y plus this times this quotient, which is x minus y. Now y in this case is greater than x over 2, so this whole term is less than x minus x over 2. Okay, because you're subtracting off a bigger number here than x over 2, which is x over 2. Okay? So mod xy is less than or equal to x over 2. Okay, so every 2 calls, the size of the argument drops. Okay? Okay, so we showed how to efficiently tell if there is inverse. I still haven't given you a way to compute the inverse. Right? It's sort of I was a little fishy here. Now I've done this math thing. I was like, well, now you could at least tell if there is one. I haven't told you what it is. Right? The algorithm didn't produce the inverse. Okay? So what we're going to do is we're going to use the extended GCD algorithm by Euclid, which extends the algorithm to find the inverse. Okay? So it computes the GCD in x, y, and O of n divisions. Just to remind you, for x and m, if GCD of x and m is 1, then x has an inverse modulo m. Okay? Okay, how do we find the multiplicative inverse? So this is the key. So he made this theorem where if any x and y, their integers a and b, where ax plus by equals d, where d is the GCD of x and y. Okay? So in some sense, it's a little hard to parse, but think about it a little bit. X and y are both multiples of d, so you know the expression on the left is some multiple of d. Right? D is the GCD of x and y. So the thing on the left is some multiple of d. What the theorem is, the power of this theorem is saying that the thing on the left can actually be the small bd, the minimum multiple of d. Okay, other than 0. Okay? Make d out of sums of multiples of x and y. And x and y are multiples of d. So at least it should be maybe possible. Okay? So what is the multiplicative inverse of x mod m? Say you have this theorem. What is the multiplicative inverse of x mod m? By the extended GCD theorem, when GCD of x m equals 1, d becomes 1. Right? So I'm just plugging in 1. And I'm plugging in x and m for x and y. I get ax plus bm equals 1. Do you guys see the multiplicative inverse of x? What's the multiplicative inverse of x? Do you see it? Well, let's take a mod and put it out there. Okay, I'm just going to go in this mod m, right? So I'm going to put a mod m there. So ax plus bm is equal to 1. That's the same as ax equals 1 minus bm, which is equal to 1. Right? So what's the multiplicative inverse of x? Right? It's whatever I multiply a by to get 1. I mean x by to get 1. What did I multiply x by to get 1? A. So a is the multiplicative inverse. So this theorem gives us what the multiplicative inverse is. We can pull out the multiplicative inverse. Okay? If I can give you a and b that satisfy this equation for x and m with GCD 1, then I can give you the multiplicative inverse. Okay, so for x and y, this is an example solution. I'm taking 12 and 35. So 3 times 12 plus negative 1 times 35 is equal to 1. Okay? So A equals 3, B equals 1. So now what's the multiplicative inverse of 12 mod 35? It's A, right? This is A. Which is A. Is 3. Is that true? 3 times 12 is 36, which is 1 mod 35. Okay. Okay. Okay, so let me just give you, I probably won't be able to prove it, but let me give you the algorithm. Okay, so here's what we did before. What happened? 35 to 12, we did that, right? 12 is the first argument, so it's the same. So in some sense, what are we doing here? We're going to build 1, or D, out of some multiples of x and y. Okay? And we start with x and y. Okay? Then we get to this point. We get 12 and 11. Now 12 is a multiple of 12 and 35. Is 11 a sum of multiples of 12 and 35? Is it? It is by this process, right? You took 35 and you subtracted 12 a bunch of times. That's what that division does. That's what that remainder does. So this second argument is also a sum of multiples of 35 and 12. Okay? And so on. Then what do you do here is the second argument is now a sum of multiples of 12 and 11. Now 12 is what you originally wanted in your system, but now you have 11. But 11, you can express as 35 and 12. As a difference of multiples of 35 and 12. Okay? How do we get 11 from 35 and 12? Like that. So there, 11 is a sum of multiples of 35 and 12. How do we get 1 from 12 and 11? Like that. But we wanted 1 to be the sum of multiples of 12 and 35, and now it's only a sum of multiples of 12 and 11. But the 11 we can go plug back in, right? And then we plug back in 11 here, and we do that. And now I have 1 being the sum of multiples of 12 and 35. And that's what I wanted, right? I wanted to take x and y, and I wanted to produce a sum, something times x plus something times y, which is equal to the GCD. Okay? Which this is an example of. Okay. And now you can simplify and collect up all the terms, and that's what you get. Okay, so it's just that this algorithm it's actually very trivial to prove everything, but it's sort of hard to see where it came from, so I wanted to go a little slow on that. But here's the algorithm. Okay, so I will... Yeah, so okay, I will let you go. I will do this on Thursday.